Hello, and welcome back to our second lecture on classical machine learning. If you're just joining us, my name is Amira, and I'm a researcher at IBM doing research in quantum machine learning. And today, what I want to take you through in this lecture is just some examples of classical machine learning models. So we'll cover them at a very high level, and this in no way is an exhaustive set of resources for classical machine learning, so please refer to some of the suggested readings, like the Deep Learning book by Ian Goodfellow and a few other authors, and get yourself a little bit more familiar with the details of what's exactly going on in classical machine learning. Now, just a recap of what we covered in the first lecture. So in the first lecture, I gave you some of the ingredients that are necessary for machine learning models and machine learning contexts or tasks. The first ingredient is crucially data. And data, as we discussed earlier, can come in many different types of forms. So we can think of data in the form of images, of videos, spreadsheets. It can be numerical, categorical. And understanding the type of data that's relevant for your machine learning task is really important. So data is crucial, and it's also needed to train models to see or recognize or understand patterns and structure that exists in real life and in nature. The next ingredient then, of course, is the idea of having a model. And we discuss some basic ideas for models, and what's important about models is that they are parameterized in this setting. So in machine learning, our models that we try to use to approximate true relationships that exist, they depend on some parameters, and these parameters are the things that we can tune and tweak and train and optimize such that our model gives us a very robust prediction or output or target distribution that we're trying to approximate in real life. Once we have a model and we pick some sort of parameter set for it, then we need to be able to score our model, to assess our model and understand exactly how good it is. And this is where this idea of a cost function comes into play. A cost function simply takes the predictions of our model and compares it to some target output, some target labels or distribution that we are trying to approximate in real life. And the cost penalizes our model when our model is very, very far off from reality. So if we give our model some data and our model tries to fit a task or do a task that fits this data, and if it doesn't do that well, then our cost function is designed such that we penalize our model for the mistakes that it makes. And then the last thing that we have to kind of include in this whole machine learning optimization, function approximation setting is this idea of optimization. So if we have a model and we pick some parameters for it, we can assess its score. But then how do we go back and change our model, change the parameters such that we get a better score every time? We get a lower and lower cost value. And this optimization process is typically done through gradient descent methods. Gradient descent methods, if you remember, just involves calculating the derivative of the cost function with respect to the parameters that we use. If we calculate the derivatives of our cost with respect to parameters, well, then we can use nice algorithms like gradient descent to figure out how to optimize and additionally change our parameters in our model such that we lower our cost value. And so this is a really, really cool algorithm that I encourage you to read about. And a more successful version of it is called stochastic gradient descent, which simply uses subsets of our training data instead of the whole training data set to calculate the cost and the derivatives with respect to the cost. Okay, so now today, we can finally kind of peek in a little bit more into what it means to have a model. So we kind of discussed it in the earlier lecture, where we looked at a basic example of classifying roses and daisies. But now I want to discuss with you three basic models that are very popular in classical machine learning. And these are linear models, neural networks, and support vector machines. Okay, but before we get into the specifics of the models, I want to also just discuss very briefly a quick history of machine learning models, because I think it's rather beautiful and really gives you a sense of how far we've come in the field. So I think in 1950, arguably the first spark for artificial intelligence came from the father of computing, one of the fathers of computing, Alan Turing. Alan Turing created something called a learning machine. This learning machine really kind of initiated this idea that perhaps human-like tasks, calculating things, could be better automated. And so these learning machines were really like an idea to try and facilitate harder computations that were hard for humans to do, but were easy for something like a computer or a giant calculator to do. And so Alan Turing started this idea and this notion of getting machines to do computations and calculations that are better or in line with at least human-like performance. This then spurred an individual by the name of Arthur Samuel, who also worked for IBM, to come up with algorithms or calculations or try to train a computer to play the game of checkers. So Arthur Samuel was quite inspired by this idea of artificial intelligence. In fact, he was even known for coining this term machine learning. And he tried to create machine learning algorithms or, computations, whatever you want to call them, calculations, set of rules, such that machines could play checkers in a human-like fashion. Then in 1957, I think this was one of the most crucial, or I'd say one of the pivoting moments, right, in history for artificial neural networks and artificial intelligence, was this introduction of the perceptron model by Frank Rosenblatt. This really, really created excitement across the globe about machine learning, about AI, because the perceptron model was the first kind of neural network. It was the birth of neural networks, and this idea of trying to create machine learning algorithms that mimic the human brain was really, really something quite profound and very, very exciting. But shortly after that, in 1969, the limitations of neural networks at that time were highlighted by Marvin Minsky and Seymour Papert. And unfortunately, they were right. At that time, neural networks were a wonderful, beautiful idea, but how on earth could we actually implement them in real life, in practice? And the limitations of these neural networks were really nicely highlighted at that time. And mostly, I think, due to computational resources that were lacking. So even though these neural networks were a beautiful, beautiful idea, we couldn't really do much with them at the time. And so this led to something called the AI winter that I think persisted for about a decade in the 70s, where none of the AI hype lived up to its reputation. There was no funding anymore into AI. The research just was not delivering as fast as people wanted it to. And so this led into this slump of what is known as the AI winter. So people kind of got disappointed in all the expectations that were accompanied with AI and neural networks and all these things, but we couldn't really do anything with it at that time. Until a very nice rediscovery, ironically, of an algorithm called backpropagation. Now, backpropagation was actually created or invented in 1970 and independently rediscovered by multiple different people. But its rediscovery and application in 1986 by Hinton and a few other people is really what rediscovered, or I'd say like reinitialized, or how do I say, resparked. Yes, I think resparked is the nice word. Resparked this interest again in classical machine learning and AI, because finally, for the first time, backpropagation gave us a way to optimize and create neural networks such that we can actually start to use them in practice. So backpropagation is an algorithm that allowed us to, when we get a little bit more into it later, we'll discuss exactly what it is, but basically it allowed us to calculate gradients with respect to our cost function, and our cost function could now include models as complicated as neural networks. So we were able to do things like calculate gradients of neural networks, and this previously was rather difficult. So backpropagation was really quite revolutionary in resurging this interest in AI and machine learning. Then in the 90s, in 1995, came the idea of a support vector machine. So we had neural networks and now another algorithm, and a whole bunch of algorithms were being proposed in between. I just want to highlight a few. So one of them is support vector machines. And support vector machines is a very beautiful idea that tries to come up with a linear decision boundary. So let me highlight it. Here in this example is the linear decision boundary, and this classifies data of one particular class and data of another class. And how it does that is it trains this decision boundary to maximize something called a margin. So we'll also go a little bit more into detail about this algorithm just now, but support vector machines really came, I think, after neural networks and spurred a lot of interest because there's a lot of very nice theoretical guarantees that are accompanied with support vector machines and maximizing this idea of a margin. And these very nice theoretical guarantees relate to things like generalization error and generalization performance, which we did discuss at the end of the first lecture. Okay, then after support vector machines, now approaching kind of where we are in this era, deep learning really became feasible. Finally, in practice, we can start to implement these lovely, very, very deep, very large models, as you all would have heard of these beautiful neural networks that train extremely well, super, super large models, and their performances are great. And finally, we have the computational power to implement these, to train these models, and to use them in practice. And so let us begin then with the foundation of modeling. Everything, I think, kind of starts always with the idea of linear models. Now, what are linear models? I mean, the name itself kind of gives away exactly what the notion or the idea is, right? It's a line or some sort of linear function that is used in a machine learning setting or a task. So let's consider a very simple example to illustrate exactly what a linear model is. So let's consider the task of regression, right? So we have a regression problem and we have data that's one-dimensional. Now, what does that mean if we have one-dimensional data? Well, then if you remember from the first lecture, it means that we just have one feature for each data point. So if I have some data point X, well, this just quite simply has one entry for this data point. And let me just say this is the first data point, and we can have multiple. We can have full data set consisting of lots of samples. So we'll say n samples, for example. Now, if we have d-dimensional data, let's say d-dimensional data, well, then that means that our vectors have a higher dimension, meaning they have more entries in them. So in general, we can say this is like some very long vector with d entries in it, d features. And we can say this has d features or dimensionality d. Okay, now specifically for our regression problem, let's look at the task of predicting the height of somebody based on their weight. So let's imagine that we have 10 data points to work with. So we have 10 samples, n equals 10 samples. So we know the heights, we know the heights, which I'll label yi. These are the things we want to predict. We know the heights and the weights. The weights, we want to use the weights to predict the heights. So the weights in this example are our x's. And I'm going to drop the vector subscript or the vector notation because we just have scalar values here. We know the heights and the weights of 10 people. And now the task is if a new person comes to us, the 11th person, and we have their weight, can we actually say something about their height? So since we have a very low dimensional data set, we can kind of already plot this. We can plot and visualize this idea. So let's draw that. Let's draw the height on the y-axis, and then we can have the weights of the individuals on the x-axis. And let's say that the data kind of looks something like this, where if we have shorter people, then we kind of expect them to weigh a little bit less than people who are taller. This is a very naive example. So as we increase the weights, maybe this is due to a fact that the people who weigh more are typically taller. Okay, and so now regression tries to come up with a rule or a line of best fit, something that fits the data in the best way possible, such that we can use it as a model to then predict an answer for a new data point. So since we're doing linear regression, what happens is we try to pick a line, a linear function that goes through our data or models our data in the best way possible. Now, of course, there are tons and tons of different lines that we could choose, right? We could choose a line that goes like that, like that. And so the task of regression is really to pick the line that minimizes the error that the model makes on the data that exists. So the error, for example, is the difference between each data point, the distance between that and our decision boundary and our linear function. So if we, let's say, come up with some line that is optimal, let's say it's the one that I've drawn right here, and we use that now as our model, then if someone comes to us and says, I've got a new person, I want to know how likely is their height to be if their weight is given by this value over here. So we can then use our linear function, our linear model, and read off what their height would be. Okay, so how do we write that mathematically? Well, we say that our prediction, let's say for a new person, I, is theta, so this is a trainable parameter, times our person's weight, the ith person's weight. And now theta actually controls how to move this line, whether it should be steeper or more flat. And so optimizing thetas really involves optimizing, again, this idea of the mean square error, which is defined in this example as, since we have 10 data points, the average over our data points, 1 to 10. And this will be our prediction minus the true value. And let's subscript that. Okay, so the mean square error actually gives us these like errors that our model makes on each data point. And so we want to pick this model, this decision boundary, that minimizes those errors. It goes through as many data points as possible in the most meaningful way. And then we know if we minimize these errors, these mean square errors, we are picking the line of best fit. We are picking the line that models our data as appropriately as possible. Okay, now, what about if we have higher dimensions? So in this previous example, we could draw everything very nicely because we just had weight as our variable that we wanted to use to predict the height. But what if we had more information to use to inform us with our thinking about creating this line of best fit? So in higher dimensions, we now have vectors or data points that, of course, contain more entries, right? So we discussed d-dimensional vectors, where d is the number of features. So if we add more features other than weight, let's say now we'll include, so we still have our weight as our first feature. Let's say we'll include gender, and let's say we'll include the height of parent 1. So one of the parents of the person. Now we have 3 features. So we've got d equal to 3. And now when we write our linear model, so we try to get some prediction, we don't just have a scalar value for theta anymore. Theta can now be thought of as a vector. And in fact, we have to transpose this vector so that this formula can make sense because our data is also a vector. So if we want to write this out, we can think of this theta, this parameter set now, as this transposed vector, theta 1, theta 2, theta 3, times by our data vector. And let's just say, I'm just going to call this first feature x1, second feature x2, third feature x3, x1, x2, x3. And this, if we multiply this out, will give us a prediction. So when we have actual data, we can plug in the values into this vector here. And then we can start by perhaps taking an initial guess for our thetas. We can multiply out the answers for all our data points, check our model's performance for our data set that we choose relative to some cost function, in this case the mean square error, and then we can figure out how to update our parameters such that we get a better line of fit, a better model of fit. But now, since we're in higher dimensions, we no longer think about lines anymore. Instead, what we think about is still a linear decision function or a linear decision boundary, but it is instead not a line, but a hyperplane or a plane. So if we go to this picture, we can again draw our data in 2D, and let's just 1, 2, 3, 4, 5, 6, just drawing some sample points. And let's say our line of best fit looked something like that. But now if we go to high dimensions, and in particular this example of 3 dimensions, well, now we have kind of more axes. And if we plot our data in this higher dimensional space, because now our data will consist of vectors or entries in the vectors that are more, let's say they look something like this. What we are doing when we are training a linear model is, instead of putting a line of best fit, we're trying to find the plane that these data points lie on that best model this data in higher dimensions. And so theta in this example is now a vector, and we have to train and optimize over these vector entries. We have to find the optimal parameter set that corresponds to this linear plane that gives us the best kind of model for our data to lie on. So when we get a new data point, say something like this, we can interpret what the output should be based on the set of parameters that we can multiply now with our high dimensional data vector. Okay, so why am I telling you about linear models? And the reason I'm telling you about linear models is because they are, of course, beautifully simple and intuitive, but also extremely, extremely powerful. And they are the basis of a lot of very popular and even more powerful successful neural networks and models that exist in practice. So linear models are actually very closely related to neural networks. And let me explain why. So let's discuss the formulation of neural networks in the context of a simple example. Let's look at two-dimensional data, and let's look at the task of classification. So in the case of two-dimensional data, let's say we've got some data point, xi. Again, I'll write it as a vector, and it's two-dimensional, so we've got 2 entries, which I'm just going to say these 2 features, x1, x2. And then let's say, since we're looking at a classification problem, let's look at the task of binary classification, meaning there can be only 2 classes in the classification problem. So our yi can simply map, or let's say our y hat I can simply map to 2 values, say class 1 or class -1. Okay, so how do we think about neural networks? Well, we know that a linear model, let's write that, linear model can be nicely formulated as the function y hat equals theta times x. And we should just do theta transpose. Now, a neural network is very, very closely related to a linear model. And in fact, we can define the very first neural network was the perceptron model. Perceptron model can be written, perceptron can be written as, now we want some output, some prediction y hat, and we can write this output or prediction again as the linear model. So we have theta times our data, and then there is just one special addition of something called a thresholding or activation function. So this sigma over here is what is called an activation function. Activation. Oh, forgive my if I make any spelling errors. This is yeah, there's no autocorrect unfortunately, but an activation function can be thought of as this simple rule to threshold our values or our answers. And importantly, this activation function is a nonlinear function. So one such example could be, let's look at this function here, where this function says, if we pass it a value that's less than 0, then we just map the function output to 0. If we pass it a value that's positive, then we map it to the function value output that it is. So what does that mean mathematically? It means we can define this activation function sigma as something like this, that, let's say I'm going to call it, what should I call it? Let's call it t. So t takes in some value z, and what it maps to is max 0 or z. And this is actually known as the ReLU activation function. The ReLU activation function says, if I pass in some value z, and z is negative, then the output of my function is just going to be 0. So that's represented by this part of this drawing. But then if z is something positive, then I'm just going to map it to the actual value of z. So this is a thresholding function, an activation function, and importantly, this function is nonlinear. So this is what is meant by nonlinearities that are contained in neural networks. Okay, so that is a perceptron model. Now, what if we wanted to look at neural networks that consist of lots of hidden layers? These things that we are familiar with in practice, that we hear multiple hidden layer neural networks, and what does that mean? So the perceptron model can actually be thought of as a linear model or a neural network with just one hidden layer. So it's direct input to output with one nonlinearity. Now, a feed-forward neural network in general can be generalized as this perceptron model and a little bit extra. So let's talk about feed-forward neural networks. So now when we have the perceptron model, we can build on the perceptron model to create these feed-forward neural networks with lots of hidden layers. Now, how does that look? Well, now we can write y hat. If we wanted to add another hidden layer, what we do is we simply start with our initial model. So our initial perceptron model, I'm going to call this parameter set theta 1 now. That's multiplied by our data. And then we do exactly the same step again, where we take this perceptron output, we multiply it by another parameter set, theta 2, and then we squeeze these outputs again by some thresholding function. So this in here is the perceptron, and we're essentially kind of repeating this idea of this linear model times by some nonlinearity. So we're multiplying again by some trainable weights. I call this set of trainable weights theta 2. And then we are passing again some nonlinearity over that. And in general, if we wanted to create lots and lots and lots of hidden layers, and we just simply kind of repeat this step where we have y equal to, let's start again here with theta 1. I'm going to drop the transpose subscript because these thetas don't always have to be vectors, and squash that with some nonlinearity, multiply that by some trainable parameters, squash that by some nonlinearity, multiply that by some trainable parameters, and then squeeze that by some nonlinearity. And importantly, I'm leaving out the idea of a bias here. So we could easily add in some bias, some kind of constants to our model, and include them into the perceptron, into the neural networks, the feed-forward neural networks as well. So just for simplicity, I left out these biases, but they can very easily be added into this idea and this model. And also these are things that we train and we optimize in this neural network setting. So as we add more and more trainable parameters to our model, we are adding more and more things that we need to train and optimize, and we're also adding more and more hidden layers in our neural network formula or representation. So this is how we could write it mathematically. And don't you think it's rather beautifully simple, because it's just taking the idea of linear models, linear classifiers, and then adding these nonlinearities, these activation functions, and simply kind of embedding or recursively adding more and more, like it's just linear models, nonlinearity, linear models, nonlinearity. And I think this is really, really quite nice and intuitive to understand the mathematics of what's going on behind neural networks. But neural networks also have other representations. And so another very convenient representation is the matrix representation that we can have of a neural network. So the matrix representation, let's start by just describing a one hidden layer neural network. So I said that earlier that a perceptron could be considered as a one hidden layer neural network. Actually, I think that's not entirely true. A perceptron can be thought of as a zero hidden layer neural network, and a one hidden layer neural network we can define as such. Let's say we've got one hidden layer. One hidden layer, feed forward neural network. Okay, and so we can write this as an extension of the perceptron model, where, if you remember, the perceptron model is activation with first parameter set times our data, and then second parameter set thresholded. Okay. Now, the cool thing about neural networks is these parameter sets, these thetas, can have dimensionalities that are really, really high, meaning we can make them arbitrarily large and more powerful, presumably, because if you add more and more parameters into your model, then you should have a model that is able to pick up or kind of capture more intricate relationships between your data. So in our two-dimensional example that we have, we know that we've got our x data as this two-dimensional vector, x1, x2. So now let's look at what theta 1 could be. Initially in our linear model, theta 1 was just this vector that contained two entries. It was this transpose vector that looked something like this, theta 1, theta 2. But in a neural network, we don't have to have the thetas as vectors. We can actually specify them as matrices. So we can have, let's say, theta 1 as some matrix, and the only condition is that the matrix dimension has to agree with the input dimension of our data. So the input dimension of our data is a vector, a 2x1 vector. So we need something here that agrees with the dimensions of our data, so it can be some dimension by 2, meaning it needs to have 2 columns to agree with the multiplication of our data. So we can, as machine learning engineers, design or specify how large we want to make our trainable parameter sets. So in this example, I'm just going to choose a dimension of 3 for our first set of trainable parameters, our theta 1. And I'm going to call these values theta 1, theta 2, 3, 4, 5, and 6. Okay, so now if we had to do the first round of multiplication, we would need to multiply theta 1 by our data and then squash that by our sigma, our activation function. So if we had to actually write this out, we would have sigma into theta 1 times x1 plus theta 2 times x2. And then we could do this for all the kind of rows and columns in our matrices, right? So now weight matrix times by our data, we then have theta 3 times x1 plus theta 4 times x2. And the last one, we'd have theta 5 times x1 plus theta 6 times x2. And we can just write these. These are going to be scalar values in this example, right? Because we have our first parameter times by our first data point feature, our second parameter times by the second feature, and so on and so forth. And so we can actually just write these. I'm just going to call them H1, H2, and H3. Okay, so now once we have our values for H1, H2, H3, we can actually output them as a vector. We can call them a vector and write it like such. So the first multiplication that happens here in our model can give us an output vector here. And this output vector, the dimension of it, importantly, depends on the dimension that we specify for our first parameter set that we want to train and optimize. So we could make this vector a lot longer, a lot larger, if we wanted to increase the number of parameters that we have in our first parameter set, theta 1. All right, so this is what happens at the first hidden layer. Then we want to eventually get to our output. So let me erase now, or let me continue on the next page. Let me also copy this so we remember what we're doing. Copy and paste. Okay, so now we want to kind of understand the next part. And the next part would be, remember, this gives us our vector of H1, H2, H3. And so now we need a parameter set, theta 2, that agrees with the dimensionality of this vector, of this output. So H1, H2, H3, this is a vector that is 3 by 1. And so we can specify our second parameter set, theta 2, as something that has dimension something by 3. Now, this is our last trainable weight matrix in this architecture with this one hidden layer neural network. And remember that we want to get out of this model some target prediction. Some prediction for our model, and in this case, we have a binary classification problem. So ultimately, we want our model to map to a value of 1 or -1, depending on the input data sample that we give it. We want it to be able to classify our data correctly to either class 1 or class -1. And so the output of our model needs to be of dimension 1. It needs to be a scalar value in this example. So we need to keep that in mind when we specify, or we want to think about, the dimension of our last trainable parameter set. And so since we want our output dimension to be 1, we can specify this to be a 1 by 3 trainable parameter set. So theta 2, we can write it as a 1 by 3 object. So 1 row, 3 entries. And now I'll just call these values theta prime 1, theta prime 2, theta prime 3. And this will be multiplied by H1, H2, H3. That output we can write as theta 1 prime times H1 plus theta 2 prime times H2 plus theta 3 prime H3. And then we squash or threshold the scalar value by our activation function. And this will give us our final prediction that we obtain from the neural network, the feed-forward neural network. Okay, so not so bad, right? Just a bunch of linear algebra and matrix and vector multiplication. And what I think is important to remember here in this neural network representation is that our model, so let's write this out a little bit more neatly. Our model, which has a series of weight matrix multiplications times by nonlinearities. And I think the key thing to remember here is that the dimension of these thetas can be flexible. These are the things that depend on our input data and our output data dimensions. And then we can really choose and design how large we want to create the number of hidden layers and the number of or the dimensionality in these hidden layers, so how we can choose these vectors here, these H's I call them. And these H's in particular have a special name. They're called neurons. So these are the values of the neurons in a neural network. So hence the name neural network. And calculating these neuron values is really, I think, it depends on the data, it depends on the dimensions that we specify. And that's, I think, really, really quite interesting and also not a very easy thing to do. So specifying the dimensionality of these trainable weight vectors or weight matrices, however you want to call them, is something that goes into design architecture choices as a machine learning engineer. Okay, so that was the matrix representation. And now one last thing that I want to make mention of is the graphical representation. So now the graphical representation, which all of you would have seen a million times everywhere across YouTube videos and everything like that, it's actually very beautiful because it represents mathematics. It's actually a mathematical notation. So in our example of our 2D data set, we can do our graphical representation as such, where we have our data point x, and remember this consists of x1, x2. And so this graphical notation here is really saying that our first values is that vector, the data vector, x1, x2. And then at the first hidden layer, we can specify how many neurons we want. And these neurons are simply our H's that we calculated before with the matrix multiplication. And so when we draw these connections to these neurons, these connections represent our trainable weights that we want to optimize for our trainable parameters. So in this case, it's our theta 1. And so this is a weight matrix, and these connections are really, really beautiful because they are, this notation is really awesome because it is essentially trainable, representing our trainable weights, right? So this is really quite cool, corresponds to our theta. And then lastly, we can, in this example, write to get our output. So we want our prediction, our y hat, and then we connect our h1s to our y hat, where these connections correspond to theta 2, our trainable weights, our second set of trainable weights. So if we go back and we remember this mathematical formulation, and then we remember how we can think about our thetas as vectors or matrices, then this graphical notation is really quite compact and really quite informative because this tells us how we're designing our network, what the weights kind of look like, and what how many neurons we have. So the weights depend on the inputs and output dimension, and they also depend on how many neurons we specify in the hidden layers. All right, well, now we can talk a little bit about the success of neural networks. And neural networks, as you know, are everywhere across machine learning literature. Now, why? Why are they so successful? And there are tons and tons of different architectures being proposed, like recurrent neural networks, which are good for natural language processing. There are convolutional neural networks, which are really, really good at understanding structures and patterns of images and videos. And there are just tons and tons of proposals for different model architectures. What I presented to you in this example was one such architecture called a feed-forward neural network. But we can change the design of how we have these models. We can have, for example, connections not to every neuron. We can have something called skip connections. So we can take that and skip over layers and such. And so when we start to get creative about how we design these neural network models, we change the architecture, and this has very, very profound results on the output. Some work better than others, and there's a lot of research in understanding why and how should we design our neural network in our model such that we get models with really good performance for certain tasks. Now, why are neural networks so good in practice? Why do they work so well? I think arguably this is still kind of an open question, but a very, very large reason for why neural networks are so good is through something called the universal approximation theorem. So neural networks, importantly, obey this idea of a universal function approximator. It can theoretically approximate any function if you make the model, if you make the model's hidden layer wide enough. So if we start to add lots and lots of neurons in the hidden layers, then we can start by adding all these nonlinearities through these activation functions. We start to get out a model that can approximate any function. It's a universal function approximator. And I recommend watching this really nice video by Michael Nielsen, who is ironically a quantum computing person, a very famous one. And he gives a very nice short explanation about why neural networks are so powerful in that regard, how they can become these universal function approximators. And importantly, this is something that linear models do not have. They do not obey this. Linear models, no matter how many times you stack them on top of each other, as we do in neural networks, if you don't have those activation functions in between, if you don't have those elements of nonlinearity, then you do not get a universal function approximator. And so this is why neural networks are so much more powerful. Another very important reason of why neural networks are successful is through the idea that we can actually train and optimize them. So thanks to backpropagation, which we mentioned earlier, we can calculate derivatives with respect to our weight matrices at every hidden layer in an efficient manner. So I won't go through the details of backpropagation in this lecture, but I highly recommend YouTubing some videos and trying to understand exactly the mechanisms of how this works. And this is very nicely built into lots and lots of Python packages and software. And so computing gradients of our neural networks so that we can optimize cost and loss functions are very efficient nowadays to do, given our neural network is of a size that our computational power can handle. Now we can finally discuss support vector machines. And support vector machines are just, in my opinion, just as beautiful as neural networks and linear models. In fact, it takes advantages from both linear models and neural networks, and we'll discuss a little bit why. And let's do that in the formulation of an example. So let's consider, to understand support vector machines, the task of classification. And in particular, let's look at binary classification. So let's say we've got a binary classification problem. And binary classification means that there are simply just two classes that my model could output to. So my model could predict, let's say, class +1 or class -1 for each data point. Now, let's draw the intuition of what a support vector machine does before going into a little bit of the details. If we have some data, say we can plot it as such, and the data belongs to two classes. Let's say the +1 class is some data points that sit up here, and the -1 class is some data that sits down here. Now, a support vector machine simply says, let's do linear classification on this data. Let's separate these classes with some linear model. But, of course, there are tons of different linear models or lines that we can draw that separate these data points, right? In fact, there are infinitely many different lines that we can draw to separate the data. So how do we pick the one that is the best? So this is the idea of what a support vector machine is trying to do. It's trying to pick a model that most confidently classifies each data class. Now, what does that mean? Well, what it means is it says we choose a linear decision boundary such that the distance between my model, so this is the green line is my model. Oh, let's write that in black rather. This is my model. And we pick this model such that the distance between the model and the nearest data points for each class, respectively, is maximized. So we want to maximize, this is the nearest data point for that class, and this is the nearest data point for that class -1. We want to pick this model such that we maximize these distances to our nearest data points. And in fact, these data points here and here, the ones that are closest to the decision boundary, these are called the support vectors. The support vectors. Because our data points can be thought of as vectors, as we've discussed multiple times, and the vectors that determine our model, the best model that maximizes the distance between these nearest data points, these are called these support vectors. So hence the name support vector machines, and the whole task is to try and find this classifier, this linear classifier, that maximizes the distance between the nearest data points for each class respectively. Okay, so that's the intuition of support vector machines. Now let's discuss it a little bit more formally. So we know that support vector machines are just doing linear classification, right? So it's just simply applying a linear classifier. So how do we write this linear classifier? Well, we know that in the case of binary classification in this example, we want our outputs or our labels to belong to either class -1 or class +1. Yeah. And so we can write our model. I'm just going to call it now f of x. And we know this very well is some trainable parameters theta and times by x, which is our data. We can write this as a vector or not. And then plus some biases. So I'm going to include these biases. You can think of these as constants in your model as well that help determine how to shift this line in the space of all the lines that you can choose. Okay, so we know that support vector machine is just trying to do this linear classification task. And of course, in machine learning setting, the idea is now to find out how to pick these thetas. And particularly, these thetas will depend on the dimension of our data, right? So if our data is, let's say, d-dimensional, then theta will be also of dimension d. So this is something important. Okay, and typically this is also referred to as a quadratic optimization problem. Okay, so why is this so special? Well, in particular, this formulation that I just described in this box here, this formulation is referred to as the primal formulation. Primal formulation. And in fact, it has an equivalent formulation. And this equivalent formulation is something called the dual. So we refer to this linear model here, as we normally know it, as the primal formulation in the support vector machine architecture. So let's look at the dual formulation. And the dual formulation, before I write it, I'm just going to write the primal over here again, just to remind us, is this, this linear model times by x plus some constants and bias. And now our dual formulation can be written as, again, f of x, and this time it is a sum over our data. And now instead of thetas, we have some trainable constants, which I call alpha. And then we've got our labels in here. And now we are doing an inner product, a multiplication between our data point I and the rest of our data. And then we have, again, some bias. Now let's unpack this a little bit. What is exactly going on in here? Well, this is the inner product of the data point xi with the rest of our data, which I call x. So it's taking our particular data point xi and calculating the inner product with respect to the rest of the data. And then it's multiplying that by the ith data point's label, yi. And then we have these trainable alphas, alpha I. Now in the dual formulation, the whole goal, the task, is to now find these alphas, whereas in the primal formulation, it was to find these thetas. Now you might immediately be saying, well, why do we even look at this dual formulation, right? I mean, this looks a lot more complicated than the primal. The primal is just a linear function as we know it, and we have to search for the thetas. And you're totally right. I mean, this dual formulation looks rather complicated, but in fact, it has some very, very nice special properties about it. And it has a lot of benefits for us when we actually try to solve the support vector machine problem. So let's discuss the first benefit. And the first benefit, or the first, I say, maybe not benefit, but maybe the right word is the first convenient thing that happens, is that at first glance, it looks like we have to solve for lots and lots of alphas, right? We have to solve for n alphas because we're summing from I equals 1 all the way up until n, because we have n data points, n samples. But in fact, these alphas actually correspond, the number of alphas that are non-zero in this equation actually correspond to the number of support vectors that we have in our model. So let me draw and remind you of what that looks like. We have our data that exists and the other class here. And we draw our model, our decision boundary. Then we have our support vectors that lie there and there. And so this green line here is our model f of x. Now, what I'm trying to say to you is that solving for these alphas, these alpha i's in the dual formulation, it's not necessarily that difficult to do because the alphas, most of them actually are zeros. It's a very sparse kind of vector. And where the alphas are non-zero correspond to the support vectors. And so solving for these alphas is actually not such a pain because there aren't that many of them that are non-zero. So the number of non-zero alphas, let's just say most alphas are 0, and the number of alpha i's that are not equal to 0 correspond to the number of support vectors. And I mentioned that the primal formulation and the dual formulation are in fact equivalent. And I'm not going to spend any time explaining why the two are equivalent. This will actually happen next week in one of the lectures on kernel machines and support vector machines. Okay, so that's one advantage, is that there aren't actually that many alpha i's, non-zero alpha i's to solve for. The second is in the example of when we have non-linearly separable data. So imagine I've always drawn data sets that we can easily separate by a line. But imagine in the case where we can't do that, right? And this is an example of a picture of two data classes, and we cannot draw a line, a linear classification model through anywhere that would separate the yellow dots from the rest. So this is an example of a data set that's not linearly separable. So how do we tackle this in the support vector machine problem? Well, what we can do is we can apply something called a feature map. A feature map is a data transformation. It takes our data that exists in one space, so in this case, it is in a two-dimensional space, and it maps our data typically to a higher dimensional space. So in this case, this is a three-dimensional space, and the feature map, which we typically denote by some transformation phi, takes our data from our original space and maps it into this higher dimensional space here. So how this would look like, let's say that we can represent each data point in our original space as vectors with two entries, x1, x2. Then we can apply some feature map transformation of our data. And this will be now a vector with a higher dimension. And let's just say for simplicity that the feature map gives us x1, x2, so our first two features, and then the third entry is our features multiplied by each other, for example. So this is an example of a simple feature map that maps data that originally lives in a two-dimensional space to a three-dimensional space. And now the convenience of mapping to a high dimensional space is the hope that when we look at the data in the high dimensional space, it now becomes linearly separable. So in this case, it won't just be a line, it will be a plane, and now we can separate these two classes by this plane. And so this is the idea of applying a feature map function to get linearly separable data again. So once we do that, then we can make use of the dual formulation. So this is another reason why the dual formulation is so important. And to understand why the dual formulation is so important, we must discuss a little bit about what inner products mean. And so inner products, remember I said that in the dual formulation, we kind of have this xi transpose by x. And so let's just say in this example, we take a particular xj. So this is the inner product between the ith data point and the jth data point. And let's say the ith data point is this one over here, and the jth data point is this one over here. So the inner product actually gives us a notion of distance between these 2 points. It gives us a measure of similarity. And now when we take the feature mapped version of our data, and we look at inner products in the feature map space, so now we look at the higher dimensional space, then we can do a feature map of xi transpose and the inner product feature map xj. This inner product here also corresponds to a distance between the ith data point and the jth data point in the feature mapped space. So it also gives us a measure of similarity, but now it gives us a measure of similarity in the feature mapped space, in the higher dimensional space. And so this is really, really something that's quite important and quite cool. This is referred to as the kernel trick, which I think will be discussed in a lot more detail in next week's lectures. So when we return back to our dual formulation, remember that we could write our classifier as the sum I n samples, and we have these alpha i's, the labels, and then we had the inner product of our data plus some constants, some bias. And this is really, really cool, right? Because when we think about feature mapping our data, right? So remember, our data is not always linearly separable. So we want to map it to a high dimensional space. And let me remind you again also the primal formulation. The primal formulation was theta x plus b. Now, if we look at the feature mapped space, let's say we apply our transformation of phi to map our data to the higher dimensional space. Well, we'll end up with the dual that will look like this, where now we have phi of xi transpose and phi of x plus b. And in the primal, we will have theta transpose and then times this feature mapped data plus b. And now we can see the benefit finally of the dual, because the dual allows us to just evaluate inner products in this higher dimensional space, which is a lot easier than working directly in the higher dimensional space. Mathematically, trying to evaluate this phi of x, and by the way, phi, the feature map itself, can be infinite dimensional. And then how do you even think about evaluating the primal? Because remember, theta depends on the dimension of this object. And now if we're growing the dimension of this feature mapped x value, then that means we're growing the dimension of the thetas. And so this primal will become a lot more difficult to solve for. Whereas if we look in the dual, we only have to worry about inner products in these high dimensional spaces, which computationally is a lot more feasible to calculate in practice. And so this is really like the biggest advantage of the dual formulation. And in fact, this inner product thing here that I've kind of grouped here is called a kernel. And you'll hear all about kernels and feature maps in next week's lectures. And so this is the main benefit of the support vector machine dual formulation. And so then the whole task is, of course, to optimize and find these alphas such that we get the best decision boundary that maximizes the margin between the data points, the nearest data points for each class respectively. Okay, and with that, I would like to just lastly recap what we covered today. So we covered some linear models where we can get some predictions, which depend on some parameters and our data. And sometimes we can add a bias to help move our line, shift our line more efficiently. Then we've got neural networks, which kind of build off this idea of linear models, but importantly include these activation functions. And neural networks, of course, have different representations. We can represent them in matrix vector notation. We can represent them as tensors. We can represent them as graphical notation. And so this is important to understand that there are different architectures, different design choices, and neural networks have the important feature of being able to express any kind of function if we make them large enough. Then we go to support vector machines lastly, which we just discussed, which does linear decision boundaries to maximize the margin. And the nearest data points for each class are the support vectors. And with that, I would like to just conclude with one last slide on what you can do to prepare for the next lectures. So in today's lectures, we covered the basics of classical machine learning. Now going forward, we're going to dive into quantum machine learning. So it'd be really, really beneficial for you to cover again the basics of linear algebra, so what vectors, tensors, matrices mean, because we'll need these objects in quantum machine learning. Go and brush up again on Dirac notation, which you would have heard in the first couple of days on quantum computing. Then also I would advise getting familiar with circuit notation, because a lot of explanations about quantum machine learning models will rely heavily on the idea of circuits. Remind yourself about the deeper inner workings of cost function minimization, because this comes up a lot in quantum machine learning as well. We leverage these ideas of how to minimize cost functions in the exact same way in quantum machine learning. And then for the purpose of next week's talks, brush up on support vector machines, because support vector machines will come into quantum machine learning quite a lot. So with that, I'd like to thank you for listening to today's lecture, and I look forward to discussing quantum machine learning models with you next time.